All right, well, the recording is in progress. I don't know if everyone got that alert or if it was just me, but here we go. So welcome to this webinar by Discover the Universe on measuring the Earth with your students. I really hope that you're going to enjoy it and take something away. My name is CJ Woodford. I am an educational content developer with Discover the Universe. But I also work for the McDonald Institute at Queen's University, which is where I'm calling in from right now. We're all back on campus. I'm sure that's a new feeling for a lot of y'all who are maybe in school or in classrooms, or maybe you teach in a different setting and things are starting to open up, which is really exciting, but also, in my experience, a little daunting. I'm getting used to seeing people again after 2 years. But thank you so much for coming to the webinar. I hope that we're able to develop some interdisciplinary stuff that you and other teachers and your students can do to learn a little bit more about geometry, mathematics, history, and of course, astronomy. And so we're gonna jump right in. Well, I do want to say that that we normally ask people where they're from. It is a pretty small group today, so if you want to tell me where you're from in the chat, that might be fun to know before we get started. Or maybe even like what grade you teach, if you teach grades, or what level. Okay, we got some high school. Excellent. I have some high school suggestions specifically in these slides because I taught high school as well. I see you. I see you, Eric. From Nigeria. Wow, really pushing our global influence here. That's fantastic. I really hope that you're going to have fun with this measurement. Maybe wait another minute just in case there's people trickling in. From Croatia. Wow. Literally all over the globe here, folks. And that is so fantastic. It's a really fortunate thing that no matter where you are on Earth, you can do this, do this measurement. From Greece. Fantastic. Well, for the person from Greece, maybe you can like actually do the original experiment, which would be super fun. That would be a really big field trip, I think, though, for you and your students, but that might still be fun. All right, I'm going to get started with this. Thank you for telling me where you're from. For those of you that did message in, people from Toronto, all over the place, which is great. We're talking today about measuring the Earth with your students and specifically looking at the Eratosthenes experiment, which is relatively simple, but we just want to make sure to give you the right tools so that you can teach it no matter what level or ability your students are at. And as we get started, I just want to take a moment. I know that we have folks calling in from all over the globe, but I do want to take a minute to acknowledge that Discover the Universe is based in Canada. And we don't necessarily have one place because all of our people are kind of all over the country. But, and our programming, of course, as has been emphasized by people in the chat, is global. And I do want to take a second to say that we are really grateful and thankful to live and work on this land that is called Canada on an international stage, and to share it with the Native peoples that were the original stewards of this land and their cultures and history. This is a really important thing for us to do, and land acknowledgements are important, but they're just one step in the process of reconciliation with Indigenous peoples. And so, especially for those of you that live in North America or otherwise on Turtle Island, we do encourage you to have a look at who are the stewards of your land and who are you sharing it with. Me personally, even though DU doesn't have a specific location, it's kind of floating all over. Me personally, as I mentioned, I work at Queen's in Kingston, Ontario. And this land that I am working and living on, I also live in and around Kingston, so it works in both ways, is originally inhabited and continues to be shared with settlers like myself, with the Anishinaabe and Haudenosaunee peoples. And we're really grateful to work with them in trying to preserve this land and preserve our relationships with Indigenous communities. Again, land acknowledgement is just one step in reconciliation, and we do really want to make sure that we're working with our Indigenous communities and not just leaving it at the land acknowledgement. So I encourage you, if you don't know a lot about Indigenous peoples, especially where you're from, to take the time to learn about them. this Whose Land resource that we're providing is quite extensive, and they do have a lot of maps all over the globe. So you might be surprised at some of the information that is available about the land that you live and work on. And we always encourage learning in every shape and form, not just in astronomy, of course. And for those of you that might be calling in for the first time, maybe you got shared to this by a friend or a colleague. What is Discover the Universe? What do we do? Well, our goal is to help teachers and educators like you, hopefully everyone in the audience, by providing educational resources and training in astronomy that is both free and online. We do sometimes have physical workshops or physical things that we send out or able to provide, but largely we do a lot of things that are digital, that you can download, that you can watch, that you can share with your students, send links, etc. Because we really want to make sure that that accessibility is there for everybody, no matter where you are and no matter what your resources. I also want to take a minute to emphasize that we do have more training on the way, and this next one that's going to come up on October 5th is a live stream with Farah Alabay, and she's a fantastic presenter. She's a fantastic science communicator, and on top of just being a fantastic engineer, she's great all around. So I really encourage you to take the time to attend this live stream with Farah. I think it's going to be super cool. She builds robots that go to Mars. I mean, I can't compete with that. Measuring the Earth can't compete with building robots that go to Mars. So I encourage you to definitely check out that next training and share it around. Maybe maybe some of your colleagues have time to attend that one if they didn't have time to come to this one today. Lost my mouse. There it is. All right. So we have our preamble. Looking out for upcoming training. We know what to use. Let's get talking about what we all came here for, is the Measuring the Earth with your students, the Eratosthenes experiment. So in case you don't have a lot of time today, or you want the short, sweet, and simple version of this experiment, maybe you got papers to grade, maybe you have lesson plans to do, you have more administration stuff, or you have kids to pick up, maybe you're a parent, I don't know. What is the main takeaway? You're going to measure the shadow of a vertical rod sometime on the equinox, preferably at noon. That's going to be the easiest one. So that's September 22nd, 2021, no matter where you are in the world, that's the date. The sun needs to be up. That's the other condition. And you can then use a web tool, which we're going to provide further down the slides, to measure the distance between your school, like where you're taking this measurement with your students, and another location on Earth. We're going to share some ways on how to make that a little bit more adventurous. Maybe you get connected with a school, or maybe you already know, or maybe you already have contacts where this is going to work really well for you. But if you don't, we have tools where you can calculate distances and this sort of thing. And the only other condition on there is that there should be someone pretty much north or south of you. And lastly, there's some math involved in doing a calculation. And if that's something where your students aren't quite ready for that, or you don't have time, or you're not really sure you have time to dig into what all the calculations are going to mean, we have an Excel file that is shared in the slides, as well as in a folder that Julie is going to be sending out to y'all, which can do a lot of that math for you, all of it, and especially if you're teaching preschool or junior kindergarten or something like that, where the math is probably going to be pretty weak, which is totally fine. Or it can do bits and pieces, especially if you're teaching a lot higher grades. Maybe they can do some of the math, but not all of it. So that's our short and sweet. Measure a vertical rod, the shadow of the vertical rod on the equinox. Use a web tool to measure the distance between your location and another location on Earth, probably a school that you're going to be partnered with if you go through the Eratosthenes experiment, which we'll talk about in a second. And you can use the provided Excel file to do all the math. So that's a short and sweet version. If you have time to incorporate more people into this, especially more teachers or educators that you work with, I think that this is a really great opportunity to bring in a lot of things. So the Eratosthenes experiment is kind of an ancient experiment where someone over 2,000 years ago did this calculation, did this experiment, and realized it worked, and actually got an answer that was super, super close to the real circumference of the Earth, which is fantastic. So, the diameter rather. So this is a really good opportunity to pull in pieces of history. What was Greece like in that time frame? What was Eratosthenes dealing with? How was he able to take these measurements? What did he use? What kind of lifestyle did they have? I think that's an interesting conversation to have, so that it puts it in context. The geography of where these measurements occurred, the mathematics behind how does the geometry and trigonometry actually give you a result, and then the astronomy portion is you need to use celestial objects like the shadows cast by the sun, and how Earth exists in space are part of that as well. So this is a really cool opportunity to make it a bit more interdisciplinary. Maybe you share classes, maybe you combine classes. You have a history class right before your science class. Maybe you can combine them and do the experiment together and have presentations. I don't know what that looks like for you, but I definitely encourage you to maybe think of a way to make it really fun for both you, your fellow teachers, and your students. I think that's a great opportunity for that. Okay, more about the science side of it. So on top of being interdisciplinary, this is a real data collection. This is going out and doing a lab, really. You're going out, you're taking a measurement. If you have older students, maybe you're thinking about things like scientific accuracy, calculating errors, systematic errors. You can incorporate that sort of thing in a lab report. And that might be a good opportunity. So it's a real data collection. It's not simulated data. It's not a simulation. This is a good opportunity to get kids out and outside, definitely outside, to actually measure the shadow. You're going to reproduce a famous science experiment, which again really ties back to that history part. And you have the opportunity to have an international project collaborating with other schools. And this is what I was talking about when I say the Eratosthenes experiment. This is an actual experiment that's hosted. You can register online. Registration is open right now for the measurement that's going to happen on the 22nd, which is only next week. So if you haven't already registered for this, you haven't seen it before, I really recommend checking out the links to the Eratosthenes experiment and registering so that you can get partnered with a school. Because I definitely think that's the funnest part about this. You might create lasting relationships, or your students might create lasting relationships with the schools that they get paired with. And that removes a little bit of the legwork on you to try and pick a location to do one of the calculations. All right, so that's some of the cool things about the experiment and the short and sweet version. What actually happened and who was Eratosthenes? I'm definitely not saying that right, by the way. I tried my best, but I do not speak any Greek whatsoever, let alone ancient Greek. So Eratosthenes was, like most people at the time who spent a lot of time thinking, was a lot of things. He was a Greek astronomer, a geographer, a mathematician, a philosopher, and I'm sure there was a ton of other things that you can use to describe this person as well. Lived in very late BC, so 276 BC to 194 BC. And I just want to point out, this is a pretty long lifespan. So, I don't know what, I don't know what Eratosthenes' lifestyle was. That could maybe be a history discussion, because it's, from my understanding of that time period, that seems like a pretty long time to, have lived through. I don't believe lifespans at that point in time were as long as that. So I don't know what a secret was, but I think maybe that's worth a presentation from a student. And he was also the chief librarian of the Library of Alexandria, which is a pretty big deal. And I think what's really cool about this is that, Eratosthenes as a person was super impressive, had lots of, areas of expertise and skills that he built, but with really simple observations and geometry that we teach in really junior high, early high school in some cases, he was able to measure the size of the Earth to within something like 40 kilometers, which is super impressive. So that's what we're hoping you're going to be able to replicate with your students. And I know you're going to be able to replicate it because it's an easy experiment. All right, so what did Eratosthenes actually do to observe and do this calculation? So on the left-hand side of the screen, I'm showing a map of northern Egypt, and we have Alexandria and Syene in red circles. So Eratosthenes, for this experiment, at the summer solstice, which is a particular time of year when the sun is very high in the sky, at the time of local noon, and we're going to talk about what that means in a second, but local noon just means that the sun is directly overhead. That's the definition we're going to go with. So the sun was directly overhead in Syene, and it lit the bottom of wells. So wells are really, really deep. And so this implied that if the sun's rays could get all the way down to the bottom of the well, it was directly above them. It's right above Syene at this point in time. But when at the exact same moment, the exact same time period, same couple of minutes, while the sun is directly overhead in Syene, we're actually seeing shadows being cast in Alexandria. A small shadow, admittedly, but a shadow nonetheless. So this is a visualization of what that might have looked like. So we're taking our map and we're putting it into kind of a 3D representation here. So the sun is coming straight down in Syene, but it's coming in at a bit of an angle in Alexandria. And this might be kind of weird to visualize. So one thing we can recommend that is super easy to make is a little demo to show this as well. This is something you can show to your students. The idea is that you have two pillars, because in Syene this would have worked as well. And I'm going to see if I can show this to you. I don't have a great light source. It's a bit cloudy where I am today. But the idea is that if the Earth was flat and you had two pillars sticking up at different lengths, you would have shadows that are the same size. And I think you can see that now. I can see it a little bit on my screen. But if the Earth is round, which is, the shadows are no longer the same size, and sometimes they go in different directions. Anyway, I don't have a great light source. You'd be better off using a unidirectional light source like a lamp to showcase this a little bit better. But that is one way to show it. And the point here is just that because of the curvature of the Earth, and you don't have light rays that come straight down at the local noon or at the zenith in both locations, which is what you would expect to see if the Earth was flat. Because the Earth is round, you actually have a small shadow appearing in Alexandria when the sun is at the zenith in Syene. So at the same time of day in kind of close locations, at least in the same hemisphere, you have sun rays coming down straight in one location and coming down at a bit of an angle on the other, which creates the shadow. So this is a video of what this measurement would have looked like. You have a pillar or an obelisk in Alexandria. You have the well in Syene. Sun rays come straight down in Syene on an angle in Alexandria. And then from there, you can measure the angle that the rays are coming down in Alexandria from the shadow. You know the distance between Alexandria and Syene. And then this gives you the last image that they had here, which is we can then actually measure the angle that the shadow is making. That's actually technically the angle that represents the sector of the Earth itself. So I didn't talk quite fast enough to get through this whole video, so I'm going to show it again. Two objects, one straight ray, the other ray coming in the same direction, but it's causing an angle. This now makes a section on our circle. We know the distance between these two locations. You can then use similar angles to figure out that the angle that the shadow is making is the same angle that you see on the Earth for that same arc. So this is just another representation of it. So this angle, the angle that the shadow is making with the pillar in Alexandria, this is the angle that Eratosthenes measured. And for any of you who might teach math or maybe teach a subject that has some trigonometry that comes in it, I think that you'll be able to see where the math is going to start coming out of this. We're going to need to use some trigonometry to find this angle. But Eratosthenes, needless to say, did calculate this angle for the pillar in Alexandria to be 7.2 degrees. And we know that a circle is 360 degrees, it represents 1/50th. He also knew at the time that the distance between Alexandria and Syene, which was about 5,000 stadia, which is an ancient unit of distance, and it's about 160 meters. So what we're trying to figure out then is if we know that it's 7.2 degrees out of 360, that's the fraction of the circle that we have here. In that case, if we know that, we can use similar fractions and say, okay, well then if it's 5,000 stadia, what is actually the circumference? So you can do a little bit of quick math. We know that 7.2 over 360 is a 50th. So then you multiply it by 50. And we can then he calculated that it would be about 250,000 stadia for the circumference of the Earth, which is about 40,000 kilometers. And we know now with more accurate measurements that the circumference of the Earth at the equator, important because the circumference of the Earth isn't exactly what it is at the equator all over. Earth is a little pear shaped, which is weird, is 40,075 kilometers. So we got it within about 75 kilometers worth, which is incredible considering you're measuring an angle that a shadow is making at high noon. That's the whole experiment. So how are you going to replicate this with your students? Most of you, I assume, are not going to be able to find an obelisk in Alexandria and also the well in Syene and do this exact measurement. So what do we do instead? I also see that the chat is a little active. I'm just going to check it. Okay, I don't see. Oh, okay, so join us why at the equinox. So we're going to get into that in actually, I think the next slide or maybe the slide after. So we are going to get to why at the equinox. So the conditions. You need 2 observations from different locations on the same day, and realistically on the same, close to the same time as well. You take the measurement when the sun is at its highest point in the sky, which is local noon. Whoops. And the locations need to be at the same longitude, which is your north-south lines, as much as possible, and also far from each other, because you can imagine it's going to be hard to distinguish the lengths or the degrees as when you start counting in things like systematic uncertainty and the tools you're using, blah, blah, blah. If you take 2 places that are really close together, your shadows are going to be pretty similar. So that might be hard to distinguish a difference there. And then it's going to be hard to do the calculation. You're going to have a ton of error to account for. It's not on the slide. So the steps to this, find the time. So in order to do these three main steps, you have a bunch of smaller steps. You have to find the time of local noon on the equinox at your location. So this is when the sun is at the highest point. So the reason why we say the equinox is that the sun is going to be at the highest point in your sky on the equinox. It's going to make the calculation a little bit simpler for everybody to do it that way. You can certainly do it on a different day, but you're going to have, there's a couple of, how do I say this? There would be some corrections you'd have to make to that measurement, and we don't really include that in this version of the experiment that we're presenting here. In the same vein, you also don't necessarily need to be on the same north-south line to do this calculation, but you'd have to then account for the fact that you're not in the same north-south line on the Earth. You'd have to incorporate a little bit more consideration on the geography. So we're trying to keep it relatively simple. So in the spirit of keeping it relatively simple on everyone, it's recommended to do it on the equinox, but you can do it at different times of the year. You can do it not necessarily on the same north-south line. It's just there are other things to consider when you take in those considerations. All right, so we're find the time of local noon on the equinox at your location, where the sun is the highest point in the sky, because that's going to be the closest thing to the zenith you can possibly do, very much like the Eratosthenes experiment in days of old. You're going to measure the shadow of a stick at that time, kind of thinking about that obelisk in Alexandria. That's what we're doing. Calculate the angle formed by the shadow from the stick, and then collaborate with another school at a similar longitude, so north-south line, or use the data for an imaginary school at the equator, in which case you can assume that their shadow doesn't exist because it's at the equator on the equinox, and the angle is equal to 0. So this is the part that's important about the equinox, is that the shadows on the equator at what is the equinox? Let's take a step back. The equinox is when the sun is directly above the equator, right? That's why. So this gives you the simplest setup possible geometrically to do this calculation. And that's, again, why we want to do it on the equinox, because we're removing some of the other factors that you would normally need to consider when you're trying to measure the size of the Earth based on the shadows of a stick. And then from that data, you can then calculate the circumference of the Earth. So you have 5 main steps. And for the 2 that have calculate in front of them, if you're a little bit nervous about that, or you think that your students might not be very interested in it, they don't have the ability to do it, they're in a younger grade, whatever the case might be, we do have an Excel spreadsheet that's being shared with you that you can use to do some of those calculations or all of those calculations instead. So lots of opportunity there. Chat again. Okay. All right, so let's start with step number 1. Find the time of your local noon. This is not 12 noon. This is local noon, which is when the sun is at its highest, which is not necessarily when the 2 clock hands are together at 12. A little dumb, but that's why it is. So what we're trying to do is not necessarily say 12 noon. We're saying local noon is when the sun is at its highest point in the sky. So why this could be the case, again, it depends on where you are. There are a couple of different factors, but big ones would be the daylight, your daylight savings zone, wherever you might be. Daylight savings tends to be a pain in a lot of ways. Your position in your time zone, the time of the year that you might be in. So all of these things have an effect on why the sun isn't exactly overhead at the zenith when you have, you know, people noon. Time is kind of imaginary, honestly. So, you know, these 24 hours in a day, these hours on a clock, they're human constructions, and the sun doesn't have to obey that. It's its own thing. It doesn't really care about our timekeeping. So we're saying that we follow the sun's rules in this case for this measurement. It has to be when it's at its highest point. Fortunately, we have some pretty cool tools that you can use to actually look for that. And one of them is Stellarium. So us at Discover the Universe, we're big fans of the technology Stellarium. You can download it for your desktop, or you can use the online version, whichever works best for you, at stellarium.org. I think that's all linked as well in the notes, and it's on our website everywhere. But one thing you can do here is use Stellarium to find your local noon. So what I have shown here is a screenshot of Stellarium that's showing a green line down the center. That's the meridian, or where the sun is supposed to be at its highest point. But this is showing it from my location, Kingston, on September 22nd, which is the equinox, at 12 noon exactly. And you can see it's not at the meridian. It's not at the highest point in the sky. So I need to find it. So one way you can do it, again, Stellarium is one way. This one might be a little faster because it gives you an answer right away in a digital format, is the NOAA solar calculator. Link is on the screen. Link is also in the notes, I believe. And how you use this one is you move this little red marker to your location. And as you can see, I've moved it to my location. You select the date that you want. So you're going to put in the 22nd of September, 2021. Be careful of the year. You might want to make sure you got 2021 in there. And what you're going to find is the answer here at solar noon. So solar noon is the one you're going to want to look for at the NOAA solar calculator. So for me, my solar noon here in Kingston is going to be at 12:58:28. I will say that you probably don't need to worry too much about the second that you take the measurement, but definitely try and get it within a few minutes of your solar noon to try and minimize that error as much as you can. But of course, as long as it's around there and you're not taking the measurement exactly at noon, if that's really not your solar noon, I think you're going to be fine. The other way you can do it, as I mentioned, is using Stellarium. This is a little bit more dependent on your ability to use Stellarium and your familiarity with it. This is actually a video that Julie's done to show how you can use Stellarium to find your local noon. So I'm going to play this. If the sound doesn't come through, that is okay, because this is largely per visual instruction. Okay, so Julie's saying there isn't any sound. So the idea here is that you have to tell Stellarium where you're located, and you have to pick the right date. So to find the equinox, you got to go your date and time window. Then it comes up with a little pop-up. So she's just showing that's what the sky looks like today, but that's not the date or the time that we want to find. So you move it to the date and the time you want. Notice that this was last year, 2020, so you'd actually make it 2021. And so what Julie is showing is that for those of us who live in the Northern Hemisphere, especially in Canada and the United States, you would expect the sun to be at its highest point when it's directly due south. So you try and estimate it a little bit. She stopped here at 12:23, then turned on the system of coordinates. And the idea is that you move the time to try and get it to the 180 degrees. So right in the center, highest point. If you click the sun, it'll also tell you some of the details that it has. And in particular, she's pointing out the azimuth slash altitude, and you want it to get to 180 degrees there as well. As close as you can. Again, as I said, with the NOAA calculator as well, it doesn't have to be exact. You don't have to take the measurement exactly at your solar noon or your local noon. It can be approximate. I would say within a few minutes here and there is totally is a very acceptable error window. You just don't want to be taking it like an hour before or an hour later. That might be a little bit too much for you to get an accurate measurement. So that's two ways you can find your solar noon. You can do it a little bit more manually by hand in Stellarium, or you can use the kind of digital output calculator of the NOAA calculator. All right, and then again, just showing you again how I found it. The idea with Stellarium is getting the sun at the 180-degree point in the Stellarium software for this particular map, and it gave me the exact same number the exact same time rather that I got from the NOAA calculator. So they're equivalent. They should give you very, very similar answers, if not the same. Whichever one you like best or whichever one you're already more familiar with is what I would recommend going with. All right, so now we know what our solar noon is. We know when the sun is at the zenith, when it's the highest point in the sky. Now we have to measure the shadow of the stick, which sounds like the easy part, and in my opinion, it is. So you know when your local noon is on September 22nd, you want to measure the shadow of the stick. So what we're recommending, because you probably already have it, is a 1 meter ruler, like the old school teacher. I don't have one with me, unfortunately. Meter sticks that usually sit on the chalkboard kind of deal. Those would be ideal. If you don't have a 1 meter ruler, that's totally fine. You just need some sort of column, rod, stick, etc., a vertical thing that you can stand up and take a shadow of, so that you can also measure the length of. So this might be a Lego tower. Maybe you and your students spend some time beforehand building these rods. Maybe it's I don't know, maybe it's a column of some sort that you have lying around a music room in your school. It really doesn't matter what it is, as long as you can measure the length of that rod either before or after you're measuring the shadow. That's all that really matters. The 1 meter ruler is just really accurately measured to be 1 meter. And again, it minimizes the error that you can have in this experiment. That's why we're recommending it, but you can really use whatever you have that you can stand up on one side in either a brace or on its own. Oh, and to answer Josiah's question quickly about finding your local noon. So the 180 degrees is not specific to Kingston. That is in general for everybody. The sun is at the zenith everywhere at 180. It's not always due south. So for anyone who lives in the southern hemisphere, as opposed to me who lives in the northern hemisphere, your sun should appear in the north, which is really weird for me to think about. I don't know if I've ever even been in the southern hemisphere. So your direction won't be the same, but the 180-degree location for your zenith, for your local noon, will be. And of course, if you're not really sure about that, the NOAA calculator will give you a direct answer regardless. So either way. And Joanne just had a question. I might as well answer it now that I'm here. This can also be done at the spring equinox, and the Eratosthenes experiment, the online portal that'll connect you with a school to do a measurement together, they run it twice per year. They do one in the fall and one in the spring. And there will be a time to register. It's just because they're running the the collaboration and the matching right now. They haven't posted when they are going to open their registration, but whenever the spring equinox is, I don't know off the top of my head, that they'll be opening it again, and they'll have lots of resources there for you again too. Oh, and the links need to be resent. Julie, if you don't mind resetting the links, that'd be great, but we can also send them at the end too, folks, if you missed it earlier on. All right, back to the stick. So as you can see, we have a student, a student here who doesn't appear to have a meter stick, but has some sort of stick that was able to stand up on its own. And they are measuring the shadow that the stick is casting on the ground. And what's also really cool about this is that if you're doing the Eratosthenes experiment route and getting matched with a school, I definitely encourage you to register with the Eratosthenes experiment. And then you can also do a competition where you submit photos of your students and you having a great time doing the measurement and learning about, you know, all of the disciplines that are involved in this. Okay, so you've got your local noon and you took your measurement. Where do we go from here? Well, now you have to calculate the angle formed by the shadow. And this is where if you are not comfortable or your students don't have the ability or it's not appropriate, you don't have time to do this calculation with your students or ask them to do it on their own or anything like that, you can use the Excel calculator that we have provided. But for those of you who might want to do it with your students, this is a quick summary of how you could do it. So the sun is beating down on the stick and the stick is of height h, and it creates some angle theta with the rays of the sun, and it creates a shadow of length s, just describing the picture for you. And what your students have measured is the length of the shadow, which is s, and you should already know either before or after the experiment the length of the stick, which is height h. And again, for anyone who's a math teacher, I'm sure you see what comes next. We're going to use our great trigonometry skills to calculate the angle of theta, because that's what we really want here. Kind of thinking about that 7.2 degrees that Eratosthenes measured, 2,000 some odd years ago. So we're going to use the tangent function, which is opposite over adjacent. If we're looking for angle theta, our opposite is length s, and our adjacent is length h, or height. And then you take the inverse function, which is going to be arctan of s over h. So I can see a couple of ways that you could introduce this to your students. For students that might have a higher math ability, be in high school, et cetera, it might make sense to get them to figure out how they're going to calculate the angle. You can say, we need the angle. We took these measurements. How do we find it? Or maybe you get them to imagine, what do you need from the experiment? Maybe you don't even tell them that they need to measure the shadow. You just say, how would we find this? Okay, like maybe you just review what Eratosthenes did and you're saying, he found an angle. How did he do that? You can really frame it in whatever difficulty level you think is appropriate. I really like leading students through calculations like this, so I would probably go with the really hard version and then just painfully tease it out of them what they need to do, but you do you, it's your classroom. So in this case, eventually what you do want them to get to is finding theta through the arctan. I'm sure there are other ways to do it as well. You can make it as adventurous and as fun as you want. And as I mentioned, if this is not something that's appropriate for your students, it's something outside your curriculum, or it's they haven't covered it yet, or you're not comfortable with them doing it, we do have the Excel spreadsheet that can do that calculation for you as well. You can also draw the triangle to scale and then measure the angle with a protractor. So if you have a really big rod, you're going to need some really big paper to draw that triangle, but you totally can, and that can be really fun, especially for students who are learning how to use protractors. Oh, and again, there's probably tons of ways to do this that we haven't thought of, and we'd love for you to try them out if you can think of one, and definitely share it back with us. We'd love to learn how people are reinventing this experiment. Okay, figure out solar noon. We measured the shadow of the rod and we know the height of the rod. We use that to find the angle that the sun's rays are making with the rod, which we did through trigonometry. So now we need to find data from another location. We've done everything we can with the information we have from our measurement from our school. So we need their angle. So this is under the assumption that maybe you've partnered with the Eratosthenes experiment and matched your school with another school, and that school has done the exact same thing that you've done at the exact same, maybe not the exact same time, but sort of close enough, and or their local noon rather, and they've measured their own angle. Or if you don't have an opportunity to do that, or you don't want to, also fine, then you can use the value for an imaginary school, which is along the equator, on which the angle is 0. So you can do that too. So you can either take an angle from another school, or you can assume an angle of 0 if you're assuming a school on the equator. And then you also know the distance, because you can use some of the tools we're going to talk about in a minute to find that distance from your school to the equator, if you don't already know it offhand, which would be wild if you did. Maybe you do, I don't know. So this is answering again a question we had earlier, but now we have pictures, which is fantastic. So why do the experiment at the equinox? So at the equinox, the sun's rays are coming directly perpendicular to the equator. So these are the sun's rays. It's directly in line with the equator. And it's coming in and it's making a right angle at this point of interaction with the equator itself. So this means that that angle that you would expect schools along the equator, close to the equator, to have for their rod would actually be 0. So the assumption we made in the previous slide would be true. If the sun's rays were coming in at a different angle, like say this way or this way, which will happen at other times of the year and in between solstices and equinoxes, then what you would need to account for is that angle that the sun is making with the equator, or with like the tilt that it is away from Earth, or from our equator rather. So totally doable, but you need to account a little bit more of the orientation that Earth has in space at the time to do it accurately. Okay, so using the data from another location. So if you have the, regardless of whether you're doing it with another school or whether you're doing it from the equator, you still need to figure out the distance between you and that other school, or your school and the equator, regardless of which way you go. So you can use a couple of different mapping tools. This one's from the National Geographic. And in this case, you would use their line tool right here. And you would just draw from your school to a school that in this case was in Columbia. I don't know. So this one is from Southern Ontario to Columbia. And it tells you the distance right here, about just over 3,100 or just under 3,200 kilometers, miles. Wow. Okay, no, you want to use this other value, this 5,001 for kilometers. I do anyway. We use the metric system. So that's one way you can do it. You are going to need to be able to pinpoint it pretty good, but you don't have to get the exact geographical coordinates of the schools. It can be somewhat approximate as long as the distances are mostly correct. That's what we're looking for here. Another way you can do it is use the Google Earth tool. They have a measuring tool as well, very similar, and you just draw a line from your school to the other school, and it'll tell you the distance as well. This little drop down that it gives you is for changing the unit of measurement. So if you don't want it in kilometers, you want it in meters, or you want it in miles, you can change it there. All right, I just noticed the chat has also lit up. So I'm gonna, before we talk about calculating the circumference, I'm gonna leave it on calculating the distance. Okay, these are the links, great, okay. So again, found when solar noon was, took the measurement on solar noon, took the measurement on the equinox at solar noon, figured out the angle that the stick makes with its with the sun's rays from the length of the shadow that you measured, paired with a school, or decided that you were going to do it based on an imaginary school along the equator, and then using one of the tools I've just indicated, or something else that you know of, you measured the distance between your school and the equator, or your school and the school that you've been partnered with. So now we actually get to the juicy part, which is calculating the circumference of the Earth from all this information that you've gathered with your students and calculated and so on and so forth. So what we want to do is compare the arc of the circle that you've measured between you and the other school with the full circumference. Now, math diagram. What we're seeing here is, I don't want to show that yet. What we're seeing here, we're assuming that you are at point A, or you're at point B, you're at one of them. And so let's say for the sake of argument that you are at point B. You're this one, you're further north than school A. Okay, so if you're further north than school A, you're point B. Your angle is theta B, which is this big one. This big one from the center of the Earth, theta B. This is your angle that you calculated in the first 4 steps, in the first 3 steps rather. The other school, school A, which is a little further south than you, calculated theta A, which is the angle from the equator to their location. This is a similar, so these angles are the same as the shadows and the shadows that the rods cast, because we're measuring it on the equinox. If we were not measuring on the equinox, this would not be completely correct, and why you would need to account for where the sun is in the sky and how it's tilting and Earth's orientation in the solar system at this time of year and so on and so forth. So this part is where measuring on the equinox becomes really important, because we couldn't make that, not necessarily assumption because we know it's true, but we can't say that that's true, that the angle you measure is actually the angle from the equator to your location. In this case, because you're measuring on the equinox, we can. So that's the motivation for the equinox, big time. All right, and then what we also measured is the distance between these two schools, which is distance d. In this case, theta b is bigger than theta a, and we can classify this little section as theta b minus theta a. You'll also notice that this angle corresponds to this arc of d, which is the distance we measured. And this is exactly the setup that Eratosthenes had when he calculated the circumference of the Earth. So now we can actually do some comparisons. And this is essentially the same formula we had in the first few slides with Eratosthenes' experiment. We're saying that theta b minus theta a, theta b is the measurement that you took, theta a is the measurement that the other school took, the angles that you found. And we know that they are a portion of the whole circle being 360 degrees. So again, it only works if you're doing it in degrees. If you want to do it in radians, just got to convert to radians. And then that's equal to the fraction of the distance between the two schools, which we know, and the circumference of the Earth, which is c. We're calling it c. You can call it whatever you want. And so the only unknown in this equation is c, because that's what you want to find. You calculated the distance between the two schools using Google Maps or the National Geographic tool. You've calculated your own angle, or you've calculated and you got the angle from the other school. So you have this number and you have this number, and we're looking for c. So you can rearrange the equation, and this is the calculation that you're going to want to do. I'm hoping that it's clear to folks just thinking about not unit conversion, sorry, but dimensional analysis. There we go. That we have a unit of degrees on the top, a unit of degrees on the bottom, so they cancel out, and then you're left with a unit of distance. So can confirm that yes, we've rearranged the equation correctly. We have meters or kilometers or miles or yards or feet, I don't know, whatever you want to measure it in, left at the end of this equation. If you are instead using the equator as your other school, and you don't have, a non-zero value, all that happens is that between this equation and the one on the next slide is that theta a is 0, and anything minus 0 is just itself. So we can say that theta b, or in this case just theta, because there's only one angle to worry about, over 360 degrees is again the distance between your school and the equator, still kind of this distance d, and the circumference c. Rearranging it in the same way, we have a little bit of a simpler equation, but it's doing exactly the same thing and the same dimensional analysis. Degrees over degrees cancel out. We have a unit of distance left. We're doing good. So that's, again, a little bit more motivation for doing it on the equinox, as well as how you would do this calculation with your students, either if you are working with another school or if you're not. And I just walked through it, maybe painfully slow for some of you, and maybe even not in enough detail for others. I'm happy to take questions, by the way, on the math. I think that it's worth, especially for students that you feel are able to have the discussions or are ready to have the discussions on some of these more tricky pieces, like why is it on the equinox? Like maybe that is a good question or a good discussion to have with your students when you get to this stage or as you're planning your experiment. Maybe you ask students to figure out, okay, this is what we've done and this is what we want to get. What is the equation we need to calculate it? Maybe you get them to calculate this equation or to figure out this is what they need. Or maybe you ask them to kind of draw something similar to what is being drawn here to prove that this is actually the way that we should be calculating the circumference in this case. There's a lot of different ways that you can spin this, and it totally depends on how you like to move your classes and the ability and interest of your students. But I would recommend not to just do the calculation. If you have time, I always recommend to do some discussion with your students to get them a little more engaged on why are they doing it. We don't want them to be little factories. We want them to, think critically, logically, and to question everything around them, because that's the whole point of experiments, am I right? So got to pretty much the end of the 5-step method for the Eratosthenes experiment. We've gone all the way from figuring out when do you take the measurement to what do you do with the measurement and finding the circumference of the Earth. I'm really hoping that when you do this with your students, you're going to get something close to the 40,075 kilometers that we know the circumference to be. And then that also opens the discussion on, well, if you don't get close to it, well, why not? What happened in your experiment? Were you accounting for errors and blah, blah, blah. I think that's also a really good discussion to have with your students as you go through it, especially for students who might be in classes where that's really important for them. So perhaps if you're teaching a physics class or a chemistry class, or if you're teaching shops, something like that, where being accurate is really important. Where did the errors pop up, and why do your students think that you didn't get an answer that was exactly right? I think those are excellent conversations to have with your students as you're going through this. All right, so the Excel calculator. This is what it looks like, which if you open it, you can see. And you still have to do the finding your stuff at local noon. You still have to measure the height of your stick and the length of the shadow. And so really all you need to do is enter the stuff in these top two yellow boxes. So you need to measure the height of your stick and you need to measure the length of the shadow. It'll give you your angle in degrees. And from there on, you're going to need to fill in what was the angle from the other school, and then it'll spit out everything else. Or you can say just circumference with the equator, and you'll have to give it the distance between your school and the equator. So steps 1 through 4 are still very relevant, minus step 3, because it'll calculate the angle for you. So steps 1, 2, and 4, I guess, are the most important. The height and the height of the stick, the length of the shadow, and the distance between you and the school, the distance between you and the equator. Those are the most relevant for the Excel spreadsheet. So if you're not going to be doing any of the calculation yourself, or you don't want your students to do any of the math part, you want to kind of use the Excel calculator as a way to bypass some of that stuff, you're still going to need to do steps 1, 2, and 4. Of course, maybe you're going to do 1, 2, 3, 4, and then skip 5, whatever you feel is best for you. That's great. But you're definitely going to need 1, 2, and 4 at the very least to use this Excel spreadsheet. And then it'll give you the circumference, and it'll also give you your error percent, which is, again, something you can ask your students to calculate if you're in a lab experiment mindset. Otherwise, it'll give you this in the Excel calculator. So just showing it with some values. Let's say you did use a meter stick and the length of the shadow was 103 centimeters. We get our angle, which is 45.8 degrees. There's a school that was partnered that only had an angle of 4.2 degrees. We know that the distance was 4619 kilometers. That gives us our circumference here, and our error percent is only 0.26%. So when you look at these numbers raw, they're like, oh wow, I didn't get as close as Eratosthenes. Wow, how did I do worse than someone that lived and died in BC? Not British Columbia, but like BC timeframe. But even then, even if there's reasons why your measurement wasn't as accurate as it could have been, etc., it's still a pretty low error percent. And I think that's what's so cool about this. Do we add the angles of the schools are in different hemispheres? Oh, that's not something we talked about. Josiah, I'm going to come back to you. Yeah. So I read that as subtract for some reason. So you add the angles if you're in different hemispheres, and you subtract them if you're in the same hemisphere. Yes. So I think the best way to do that, to think about that, would be to kind of refer back to this diagram. So instead of drawing the angles like this, you would draw them the other way around. And once you have it in there, I think it's a lot more clear what happens, because in this case, I guess an easy way to remember it is if your angles are going to overlap, you're in the same hemisphere, you subtract. If your angles don't overlap, they add, you're in different hemispheres. So then that's how that would work. Sorry, I didn't even think about that. Thank you so much for bringing that up. Yeah, exactly. So you're looking for the angles between the places. So if the angles are overlapping, you subtract them to get the right angle. And if they are not overlapping, you're in different hemispheres, you would add them. So I'm really, really glad that came up. Thank you so much for asking that question. All right, so thinking about having schools in different hemispheres, you're not just looking at the equator. where does this international collaboration part come in? So this is, again, the Eratosthenes experiment that we've been emphasizing, kind of heavy hitting it. The next equinox is September 22nd of 2021. This year, it's next week. And the registration is open. So if you have the opportunity and the ability and the time to do that with your students, I think it would be worth it registering. As far as I know, it's a good experience to have, and you can enter the photo competitions. I think it is fun if you have the ability to do that. But as was already asked, they're going to run another one in the spring. They kind of do it every year. They did it all the way through the pandemic, as far as I'm aware. And so if you can't do it next week, understand. You can do it in the next semester, if you're in 2 semesters, or next couple of semesters if you're in tri-semester, sometime in the spring. That's when you can plan it next. They do have a lot of countries and a lot of schools that do participate. These are the ones that have registered so far. There's only one in Canada, so it'd be really cool if anyone who is listening in from Canada and the United States today to actually like register for it, because it's pretty sparse. But I encourage everyone to register and really boost up these numbers, because this is a really cool initiative with, to partner with schools and to do some cool science. So some resources that the Eratosthenes experiment also has for you. So there's what we've made and provided, but they also have a lot of fantastic ideas and information there for you. They have their own lesson plans that you can incorporate into your lesson if you want to do some learning before you do the experiment or after. And they also have a whole resources section. And in that resources section in particular, there's a really, really great video with Carl Sagan from Cosmos. And he has little rods sticking on a map. And I promise you, it's a lot better than me and my little cardboard sheet. So this is a great physical demonstration if you want to bring it in for your students. But if you have an opportunity to show them this video or share them this video, I think it would also get the point across really well. All right, and with that, thank you. I hope that you enjoyed the presentation. I hope that you learned something and are inspired to do outside lab-like science experiments with your students, incorporate teachers from other disciplines into having maybe a group experiment where you talk about more than one discipline at the same time, more than one asset, some of the context behind the experiment. And that if you can't do the Eratosthenes experiment formally and get partnered with school, that at the very least you'll do the experiment with your students as your own standalone lab and just use the angle 0 at the equator during the equinox to see if your students can calculate and see what they think of that. I'd love to take any questions that you have now that we didn't answer throughout the presentation. And thank you so much for coming. If you have to run, I totally understand. It was great having you. And of course, as always, you can contact us if we don't answer everything during this time as well. All right, I see the chat. Yeah, I see some people here that say that they don't have students. That's okay. Do it yourself. Do it with your family. I've been really pushing my colleagues that I work with here at the McDonald Institute to do it with their younger kids who are doing some homeschooling right now. I think that it's a lot of fun for everyone to get involved in. So whoever looks to you for science knowledge, do it with them, regardless of whether that's in a formal classroom or that's your family and friends, or that's someone's kids that you look after for babysitting or something. I think all of that would be a ton of fun. Just again, on the equinox to minimize some of the considerations you have to have. And if you can register with the Eratosthenes experiment to get partnered with a school or partner with other people, that would be really fun too.